In this lecture, we'll talk more about general machine learning, and specifically, we'll talk about k-nearest neighbors and support vector machine, or SVM. And usually in machine learning or supervised learning, we would like to do prediction. And specifically, we want to estimate a function fx so that we can actually predict the y of a new data using the function fx. And here, y can be some real number if we're doing a regression test. For example, given some data or history of a patient, we want to predict the life expectancy of that patient. And y can also be a categorical value if we are trying to do a classification test. For example, if we're given an email and we're trying to predict whether or not this email is a spam, then the label y will be a categorical value. And also you can, this y can also be some even more complex object. For example, it can be the ranking of items or past trees, etc., etc. So usually in this supervised learning setting, it's called supervised because the data is labeled. And we usually have many pairs of x and y, where x is the vector of binary, categorical, or real value features. And the y here is a class label. It can be the binary or a real number. So usually here in supervised learning, we have the training set and we have a test set. And for example, here each row of this matrix X can be the vector of input features of a specific data point, and the corresponding label would be in this y here of the same row. And the goal of supervised learning is that we were trying to estimate a function fy on the training data x and y, and we hope that this same function fxy, it would also works on the unseen data x prime and y prime. So in this lecture, we will talk about the following two methods. We'll talk about instance-based learning and, for example, k-nearest neighbor. We'll also talk about support vector machines. So basically, the main question of machine learning in general is how to efficiently train or build a model, or equivalently, how to efficiently find the model parameters. First, let's look at the first class of methods, instance-based learning, and specifically, let's talk about nearest neighbor approach. And usually, a nearest neighbor method will work as follows. We will keep the whole training data set. We have a lot of pairs of x and y, and we're given a query example. Most probably it's going to be a vector q, and the vector q comes and we will just find the closest example, let's call it x star here, in the training set, and we're just going to predict the labels of these examples, let's call it y star. So basically we will use the labels of the closest examples as the label of the query example. And one nice thing about this is that it actually works for both regression and classification. And interestingly, the collaborative filtering approach that we have talked about in the recommendation system section is an example of k-nearest neighbor classifier. So basically, in collaborative filtering, if you remember, we will find the k most similar people to user X that has rated the movie Y, and then we'll just predict the rating YX of the user X as an average of the ratings from all those people by k. And specifically, let's first talk about the simplest example of nearest neighbor, which is one nearest neighbor. And usually to make a nearest neighbor approach work, we need four things. The first one would be the distance matrix, because if we need to use some distance metrics to decide which example is the nearest one. So let's say that in this case, we're usually using the Euclidean distance. And the second question is how many neighbors to look at. Since it's one nearest neighbor, obviously we'll only look at one neighbor. The third question is the weighting function. This is optional. And for this nearest neighbor approach, you actually don't need it. And the fourth question would be how to fit with the local points. And here, since we only have one nearest neighbor, we can just predict the same output as the nearest neighbor. So we can see here as an example, let's say that we have a lot of data points as a training set. And if we we fit a one nearest neighbor model using this data set, and this would be the regression model output, we can see that sometimes it oscillates a lot. And if the data points in the training set happens to be monotonic, the resulting regression model will actually be a step function. And this is another example where we have a different set of data points as training set. We can see that this is the results. And let's say that we extended a bit from one nearest neighbor to k nearest neighbor. So the difference is that we're now looking not just one, but k neighbors. And to fit with the local points, we will just predict the average output among the k nearest neighbors. For example, let's say that we are training a regression model and we'll just set k to 2, then we'll just find the 2 nearest neighbors, and we'll take the average label of these 2 nearest neighbors, and we'll just predict the average value. And let's say that we now set the k to 9, and we use the same data sets as we have used in the one nearest neighbor example. And this is the resulting regression model of a k nearest neighbor. We can see that the model actually, it now becomes much smoother than before. Remember, previously we have a lot of oscillation here, but now it's mostly gone. And interestingly, we can also extend the k nearest neighbor from using only k neighbors to using all of the data points. And this is called kernel regression. In kernel regression, usually we will still use the Euclidean distance matrix, and how many points, how many neighbors to look at will different from k nearest neighbors. We will look at all of them. And here comes the weighting function. In terms of the weighting function, because we use all the data points, it has to be some weighting function to decide which of those data points are more important and which of those are less important. So basically, we have a weighting function that looks like this, and we can see that basically this means the nearby points to the query queue will be weighted more strongly, because if the distance is kind of smaller, then this weight will be larger, as we can see here in this plot. And KW is the kernel width, which is basically a hyperparameter that you can tune. And how do we fit with the local points? Basically, since we already have the weighting here, we can just predict the weighted average as the final result. And here is the some sample result if we use a kernel regression. Let's say that we already have some data points here, and we use a kernel width of 10 to fit a regression model, and this is the final model. If we use a larger kernel width, and this is the resulting model, if we use even larger one, we can see that it gets very, very small. So basically, the larger the kernel is, the smoother the model will be. But you can see that when the kernel width gets too large, the model will essentially underfit. And if the kernel width is too small, the model is going to overfit the data set. And let's see how it performs if we use the data set as we use in the k-nearest neighbor. We can see that it's going to produce a much smoother regression model than the k-nearest neighbor. Especially here, we can see that it now becomes a very smooth function as opposed to the step function in the one nearest neighbor model. So one implementation detail here is how to find the nearest neighbor. So basically, we're given a set P of endpoints in D dimension, and we're given a query Q also probably in the D dimension. And we want to find some nearest neighbor. If it's the nearest neighbor approach, we'll try to find the nearest neighbor P of Q in the set. And alternatively, we can also try to use a range search. We can find one or all points in the set within some distance from Q. And specifically, if we want to run the algorithms in the main memory, we can do a linear scan, basically scan through all the data to find the k-nearest neighbor or find the data points within some radius. Or we can use tree-based approach, for example, a quad tree or KD tree. And more interestingly, we already know that we can use hashing-based method, such as the locality-sensitive hashing that we have discussed before. And furthermore, if we are allowed to use the secondary storage to handle the larger data set, can also use the trees algorithm.